In this video, we will find out why we need spanning tree protocol. Let's analyze this network diagram. As you can see, Cisco Skill switch 1, 2, and 3 are connected all together for the purpose. If one link is down, the network traffic will be redirected to the remaining links without user notice. However, it creates a loop for broadcast frames. Let's see what happens when PC1 sends an APP request to find the MAC address of PC2 in this network. First of all, PC1 have to send a broadcast frame to switch 1. Switch 1 will update its MAC address table and forward the frames to switch 2 and switch 3. Switch 2 and switch 3 also have to update their MAC address tables. Now, let's pay attention to switch 2. When switch 2 receives the broadcast frame from switch 1, it will forward the frame to PC2 and switch 3. When switch 3 receives the broadcast frame from switch 2, it has to again update its MAC address table, which causes the MAC table instability. When PC2 receives the app request from PC1, it will update its app table and respond with the app reply back to PC1. When PC1 receives the app reply from PC2, it will update its app table. Now let's pay attention to Cisco Skill switch 3. Switch 3 have to process the broadcast frame sent from switch 1, and it will forward the broadcast frame to switch 2 and PC3. Upon receiving the broadcast frame from switch 3, switch 2 have to update its MAC address table, which causes the MAC table instability in switch 2. Again, switch 3 have to process the broadcast frame sent from switch 2, and it will forward the broadcast frame to PC3, which causes PC3 to receive multiple copies of the same frame. In this case, PC3 just dropped the frame. Cisco Skill switch 3 also have to forward the broadcast frame to switch 1, which causes switch 1 to update its MAC address table and cause the MAC table instability in switch 1. Now let's pay attention to Cisco Skill switch 2. Switch 2 have to process the broadcast frame sent from switch 3, and it will forward the broadcast frame to switch 1, which again causes switch 1 to update its MAC address table and cause the MAC table instability in switch 1. And switch 2 also have to forward the broadcast frame to PC2, which causes PC2 to receive multiple copies of the same frame. And in this case, PC2 will process the broadcast frame, and it knows that it is the app request sent from PC1, and it will again have to respond with the app reply back to PC1. However, in this case, the app reply will be looped between switch 2 and switch 3 until one of the switches update its MAC address table correctly and send to PC1. So this looping frame here will be corrected. However, the broadcast storm will last forever until one of the switches reboot or one of the links go down. As you know, the broadcast frames will loop forever in this network, which eventually will bring the entire network down. To solve the problems, IEEE created Spanning Tree Protocol, or STP, and later Rapid Spanning Tree Protocol, or RSTP. STP or RSTP prevents loops by placing each switch port in either a forwarding state or a blocking state like this. Interfaces in the forwarding state act as normal, forwarding and receiving frames. However, interfaces in a blocking state do not process any frames except STP or RSTP messages. We will learn more about STP and RSTP in the next video. Let's sum up our video with the keynotes. Redundant links in an Ethernet network creates a loop for Ethernet frames, which in turn causing the following problems. Broadcast storm. Broadcast frames travel indefinitely within the broadcast domain, which consume link capacities, and it also creates MAC table instability. MAC address tables of all switches in the broadcast domain constantly get updated with incorrect entries from the looping frames, which makes the wrong forwarding decision for the switches. Multiple copies of the same frame are delivered to the destination host, which makes its responses to the same requests again and again.